Okay, so we start today's session. So today we move on to study session 3. So session 3, session 4, and session 5 are all related to the third topic, which is about the Internet of Things, right? In session 1, we have studied partially the basic knowledge about the robotics, right? And we could consider robot as a mini version of IoT. And in session 2, we have studied industry automation. So during the study of session 2, we know that inside manufacturing system, we have a production system. Inside the production system, we have an automation system. Then inside the automation system, we have a control system, right? Then we know how to design the control system with the technique learned from the control theory. Okay, so today we will move on to know how to physically construct either robot or production line, because from an IoT point of view, a production line is also an example of IoT, right? So now we may want to know, okay, physically how to design Internet of Things. Okay, so for today's session, we will only study the way how to build up the network inside IoT. And inside the IoT, actually, you have two keywords. First one is what? Internet. Second one is what? Second one is a SIM, right? So you may want to know how to establish a network, right? Or how to build up a network. Second question you may have in mind is what should be the major SIMs for us to attach to the network, right? By now, I guess you know, right? First SIM to be associated with the network should be actuator. Second one should be sensor, right? And eventually, you may want to attach computational unit to the internet, right? So then with all these knowledge and skill, eventually you should be able to construct your own version of IoT, right? So, but there are many protocols for us to design internet. So here we are going to study the basic principle at the lowest level. So it means what? This should be the universal principle. Regardless what should be the higher version of protocol or communication, at the lowest level, they will follow these two type of communication protocol, right? One is a synchronous serial communication. Another one is asynchronous serial communication. Okay, with this knowledge in mind, eventually you should be able to understand all kinds of network. Okay, so let's start with lecture 1 in today's session. Okay, so lecture 1 in today's session is to help you to understand the importance of IoT. Okay, and if you try to relate today's study with session 2, because you remember in session 2 we talk about the industry automation. Now you can start to think about this question. Okay, maybe some of you may already heard of industry 4.0. Some of you may have heard of this terminology of Industry 4.0 or Industry Revolution 4.0, right? So then what do we mean by Industry 4.0, right? And if you do not know what is Industry 4.0, at least it is very easier for you to understand what is an Industry 3.0. Does anyone of you know what is Industry 3.0? Anyone of you heard of this terminology, CIM? But anyone of you come from a mechanical engineering school? None of you. Okay, so CIM means a computer integrated manufacturing. Then what should be Industry 4.0? Answer is what? IIM. Then what is IIM? CIM means what? C means computer. IM means computer integrated manufacturing. Industry 4.0 is what? Industry 4.0 is Internet integrated manufacturing. IIM. Right? Then you can start to think about what should be Industry 5.0 or 6.0. Right? Actually, it's very easy to predict. 5.0, 6.0. Okay, clear. So you see, Industry 4.0 means Internet integrated manufacturing. So immediately you understand. In section 2, when we study manufacturing system, production system, control system, all these are examples of IoT, right? So then you should not be surprised about the jump, okay, from section 2 to section 3. Then they say section 2, section 3 are not related. Actually, it is not true, right? Okay, so but here when we focus on the study of IoT, so basically we are not just narrow down our application to manufacturing, because IoT could be applied widely to many other areas, right? Okay, so then when we study IoT, good news to you, for you to know is about this special device which is called as a microcontroller, right? Because if you look at the definition of network means what? It's very simple. A network consists a system with interconnected node channel. You have a node of a node, right? Then they are interconnected together, right? Then the question is, what should be the device which plays the role of a node? Answer is what? Microcontroller. Okay. So as long as you know what is the microcontroller, then you will be comfortable with the design of any network. Okay. So then you want to know what is the microcontroller. Microcontroller basically means a microprocessor plus input-output module. Then you look at this diagram. So this diagram is extremely simple, extremely important for you to remember. So on top you have an electronic brain. Electronic brain basically means what? It's a microprocessor, right? Then you see input module, output module, right? So this helps you to understand that the microcontroller could serve as a node inside any network. Okay, so and for our student, they will spend 1 semester to study microcontroller. Right? Then here you just spend 1 or few hours to know the basic working principle of microcontroller. Right? So in the first lecture of today's session, so we just quickly go through overview about the network system, and in particular, then we will try to know what do we mean by IoT, what are the possible applications with IoT, what should be the challenge faced by IoT, right? Okay, so let's start with the network system, okay? So in order to know what is a network system, then you need to know what is a system, right? A system basically means you have a lot of interrelated module or subsystem or module or element, okay, which work together for the achievement of a common goal. For example, a vehicle itself is a system travel, and inside the vehicle you have a subsystem, etc. Right? And then what should be the network of the system? Okay, so depends on the connectivity. If you make use of a network to link all the module, all the subsystem, all the element inside a system together, then you must put the adjective of network in the system. Okay, because the connection is through the use of network, right? But you may have a system, okay, the connectivity are purely based on the mechanical interface, electronic interface, right? It is not a network, right? So among the way for us to establish the connectivity inside a system, one particular solution is to make use of network, right? So for example, you see this robot, and typically this is a network system because this robot has a very complicated micro working system, manipulation system, eventually vision system, control system, etc. Right? So the connectivity among all the subsystems have to go through the use of a network, right? Yeah. Okay. So then, okay, this slide is helping you to think through about the scope of network in the system. For example, inside the factory, you have many machines or many robots. How to link all these robot machines together? The only way is to use network, right? In the home environment, hospital environment, school, and the city. Actually, this slide helps you to define your group project already, right? Because some of you may want to know, okay, how to identify the group project. Okay, you look at this slide, right? You start with the network system. Okay, and I guess you have seen this video before. Okay, this just remind you about that. Okay, to answer the question of what is a robot, what is a robot is right? So you will see this robot as a grounding system, manipulation system, vision system, etc. Right? Okay. So we could just quickly skip this one. And this slide showing you another example of a network system. You can connect computer, printer, or other machine together to form a networking system. It's quite straightforward, right? So in section 2, we have a study, manufacturing system, production system, etc. And this is a picture showing you landscape of a production system. So inside you can identify many robots, yes or no, and also CNC machine or computer controlling the machine. So this is a typical example of a network system in industry. And here you see the terminology of industry 4.0, right? So what do we mean by industry 4.0? Just now I already tell you the answer. So industrial 4.0 basically means internet integrated manufacturing, IIT or IIM, okay? So very simple. Then in the home environment in future, but today this scenario is not so popular, right? Except some very expensive houses, okay? But slowly, I believe this scenario will become very popular in the future. Every household will behave like a network system, right? Okay, but this gives you an idea of you to do your project, right? Then in the hospital environment, obviously you have many surgical operation theater, right? And also the room for the patient to stay. So you need to link all the room inside a hospital together. And sometimes in the city, you may have a multiple hospitals. Among all the hospitals, they also need to exchange information. Now you see, you can network all the hospitals in the city together, right? They share the data, etc. Right? Then in the school, in the same school have a lot of classroom and a lot of office, right? So how to interconnect all these rooms together and share the common data inside a school or university, etc. Right? Then slowly, in future, in the city, and more city will behave like a network system, right? Today, you can only find the network system in some major city or the city of advanced country or developed country, right? Slowly, this will become very, very popular in the future on Earth, right? Okay, then this slide gives you a definition about the networking system. But this illustration showing you that there are 5 mobile robotic arms work together. Okay, obviously you must interconnect them together through the use of network, right? Okay. And then what should be the key characteristic of a network system? It should be similar to any normal system, right? Once you see a system, you must talk about the input, output, and the relationship between input, output. But in particular, you need to pay attention on how this input, output, and the inner process exchange data. Because for network system, inside you have a lot of modules. They must pay attention to how this module exchange data. In this case, for example, you have a vision system, and suddenly you must have a control system. How exchange information between vision module, manipulation module, this one has a manipulation module, and a hand module, plus a view module of mobile base, right? So this you have 3 major modules: vision module, mobile module, manipulation module. Okay, so all these 3 major modules need to exchange data among themselves, right? So this is very, very important. Okay, but in terms of the signal flow inside a network system, so they are similar to the normal system. So you have input, you have output, then you have inner process which will transform input to the output, etc. Right? So in terms of a signal flow, nothing changed, right? So you just need to think in terms of how well support for you to achieve this signal flow inside any system, either in terms of open loop system or closed loop system. Okay, but here you need just pay a special attention to the network system, right? Because by default, when you see the network system, automatically it means what? This is a digital system. That means the signal or data flow inside must be digital data by default, right? This is the only difference. This is why now you see this 2 green box, right? And just like I mentioned, okay, what is a network? Network consists of a set of nodes which are interconnected together, right? And each node actually is a microcontroller. Microcontroller is what? Microcontroller is a microprocessor plus input-output module. What is a microprocessor? Microprocessor is what? It's a digital system. Yes or no? When we talk about computer in this context, we only talk about the digital computer. Yes or no? Right? So from here, you need to know network system must be a digital system, right? Then there's a challenge here. How to interface all the module inside a system through the use of a digital networks, right? Because you cannot impose this constraint, you cannot say every module, every element in any system must be digital system. You can still have an analog system, right? So in order to overcome this issue, now you see two additional devices appear there. Do you see this AD? What do we mean by AD? It means what? Analog to digital conversion. Do you see DA? What do we mean by DA? DA means what? Digital to analog and conversion. Okay, so these are some extra knowledge for you to know in case if you do not know what is DA, what is AD, right? And then immediately you know the requirement for us to add in these two devices is because in general, a network system is a hybrid system because inside we have a digital device, we have also analog device, right? Because we cannot impose the requirement for every module inside any system to be digital, right? Yeah, okay. So this is something you need to pay attention. Now come to this question, okay? Because since people talk about the IoT, then we just use this terminology, right? Strictly speaking, IoT is what? It's a network system connectivity. Then you may say, you may want to know how come people use another terminology, right? Answer is what? It's just to attract attention of people, right? Clear. So then we must know what is IoT. But if you look at the name, there are two keywords. One is internet, another is SIMS, right? But if we use IoT, T means SIMS. Once you see the T means what? T cannot cover human, right? So they cannot consider the network in which you will send an email. Then you cannot name such a network as IoT because you are there, John. You send an email, you browse a website, so that is not IoT. Yeah. So why we put this name just to emphasize that this is a network for us to build up a system inside. There is no presence of human being, right? There are many device or machine exchange data, etc. That's it. Okay. So you look at this video and
for the way we drive to how we purchase it, and even how we get energy for our homes. Sophisticated sensors and chips are embedded in physical data environments. Each transmitting valuable data. Data that lets us better understand how things work and work together. But how exactly do all these devices share such large quantities of data, and how do we prevent information to work? If we were improving production capacity, even city residents real-time updates on where they are, on monitoring our personal health, it's the common Internet of Things platform that brings this diverse information together and provides a common language for devices and apps to communicate with each other. The process starts with the devices themselves and securely communicate with the Internet of Things platform. This platform integrates data from many devices and provides analytics to share the most valuable data applications that address industry-specific needs. Let's start with a simple example: a car. After taking a long road trip, Rebecca notices that her check-in is not. She knows that she needs to have a car with every account, but is not sure whether it's something minor or something that needs to be attention. As it turns out, the sensor that triggered Rebecca's check-in monitors the pressure of the brake pump. This sensor is one of many monitoring processes around the car, which are constantly communicating with each other. A component in the car called the diagnostic bus gathers the data from all of these sensors and passes it to the gateway of the car. The gateway integrates and stores the data from the sensors. This way, only the most relevant diagnostic information will be transmitted to the manufacturer's platform. But before sending this organized data, the car's gateway and platform must first register with each other and confirm secure communication. The platform is constantly gathering and storing thousands of bits of information from Rebecca's car and hundreds of thousands of car sensors, building a historical record in secure database. The manufacturers have released the logic to the platform, so when Rebecca's car is in the state of the breakthrough is probably recommended level. The platform triggers will work in the home. The manufacturer also uses the platform to create and manage applications that cause specific issues, In this case, the manufacturer can deploy an application on the platform called the Asset Management System. This application knows all of the customers' cars on the road, as well as all the parts in the warehouses. It uses the data from a driver's car to offer a potential appointment time to service the car. They'll have to distribute a certified dealer and can monitor the service. What's more, the app will ensure that the demonstrates are covered under the warranty, that the correct replacement parts ordered, and then sent to the dealership so it'll be ready when she arrives. But the manufacturer's analysis does not stop there. They have also deployed a continuous engineering application that tracks not only the vehicle car, but hundreds of thousands of others, looking for ways to improve the design and manufacturing process of the car itself. If the same problem in a breakdown also an improved number of other parts, the manufacturer uses applications custom built for the automobile industry to pinpoint the exact problem. You can see that these cars are made at the same factory, use the same parts, or came off the assembly line on the same day. So what do all these pieces add to? Streamlines the inventory management for the dealer, a better, safer car for the manufacturer. And for Rebecca, it means she can be back on the road faster and get to where she's going safely. All thanks to the Internet of Things.
Okay, so this show here basically, okay, to summarize, you need to understand a car itself is a typical example of IoT, right? So it's like a robot is a mini version of IoT, and a car is also a mini version of IoT. And also on the street, all the cars can interconnect together, right? They share the information, so the manufacturer can anticipate the repair or replacement of a certain component inside the car, right? So then in future, when you drive your car, the car may tell you, when are you going to change the tire? When are you going to change this component or another component? Now you see the convenience, okay, with the use of IoT, right? So immediately now you understand what do we mean by IoT. So specifically, IoT means network system or distributed system, right? With the interconnect the sensor, controller, and the actuator. So this should be the three major things inside IoT. Okay, so we are not talking about the network of a table. We are not talking about a network of a tree, right? So here you see T specifically means sensor, actuator, and the controller. Okay, yeah. But of course, you may make all the tree in the city to be interconnect together, and you may know what you need to do the service for the plant, etc. Right? Okay, so this is very clear. Okay, now you see microcontroller is extremely important course for you to study. I do not know whether you have learned or study the microcontroller course or not. If not, maybe now you know the motivation, right? So this is extremely important course in engineering, right? Because in future everything will be interconnected together, right? So then what is the architecture of a microcontroller? Actually, it's very, very simple. You follow the blueprint of any digital computer. This is the blueprint design. This is the design solution for the major digital computer. You just need to remember there are two major devices or item or module inside. One is what? Memory, you see. Second one is what? ALU. A means arithmetic operation, and L means logic operation, right? But in between, you see control unit. That is a module behind the microcontroller. So in front, at the foreground of a microcontroller, you only see ALU memory unit, right? And sometimes we may split memory into two. You need two memory, one for data, one for program. Then you may heard of this DSP. I guess some of you may heard of DSP, digital signal processor. But what is DSP? Very simple, like just split its memory unit into two, one for data, one for program. That's it, right? Clear, okay? So, and today, the typical example or most popular example of a microcontroller should be ARM, or Cortex MCV. M means microcontroller, right? Inside your handle, you have an ARM ACV. A means application or advanced application, right? Sometimes you may heard of ARM, RCV. R means real-time application, right? So for us, it's MCV or microcontroller. Okay, so this is the most popular microcontroller for you to consider. And some of you ask this question: is there any dedicated platform for you to implement IoT application? The answer is yes, right? You can use any microcontroller. Actually, you can develop your IoT prototype. If you want to have a dedicated solution or product, this is one example. I guess this company is also quite famous, right? So you see, you have a sensor and there's no actuator. Okay, so you can plug in sensor, plug in actuator. Very, very simple. Okay, yeah. So then by now you know what is IoT. T specifically means sensor, actuator, microcontroller, right? Then, okay, in the previous video, you already see that a car is a typical example of IoT. And I have also mentioned that the robot is a mini version of IoT. Then you may want to know what else, right? How come IoT is so popular, so important? Okay, now I just quickly go through some typical example, okay, beyond manufacturing, beyond robotics, etc. Okay, so from this slide, immediately you see in the hospital environment, in healthcare, right, in smart city, in agriculture, in industrial automation, you know, right? Disaster, especially you see disaster management, right? So recently we see some earthquake, right, and the fire or something like that. How to prevent all these disaster to be occur in the city or in the country? Only solution for IoT. But recently you see a fire, okay, kill a lot of people, right? And why such thing happen? Answer is what? There's no IoT. Immediately you understand. So in future, let's say if we impose every building must have IoT, then you can prevent such an accident. They impose every building must have IoT. Otherwise, you will not allow this building to be operated. Why not? Right? To save life. Understand? Okay. So disaster management, but today we do not pay too much attention, right? Okay. Yeah. So this helps you to know the wider scope of application with the use of IoT. Okay, you should not just have narrow focus about the IoT. All right, robot is IoT, car is IoT, production line is IoT. Then our everyday life is IoT. Let's say when you do the booking, whatever, actually they are interconnected together, right? Okay. And this also is very interesting. I guess today it starts to become popular for some high or smart restaurant. You go there, you have a dining table. Actually, you can place order, right? Maybe the table itself is a touch screen or something like that, right? And then eventually, in the ceiling of a restaurant, you can monitor your behavior, etc. Right? This is another interesting application, right? And this may become popular in future, right? Okay. And this just I just play a little bit of.
Thinking about the lines of providing that they can make restaurants a lot easier and help us do it more.
When we're all students, so they're close to the budget, the idea came about because we felt that we couldn't get also really great and work price. I think all over 750 using the technology for it to be really efficient. The one that value is the consumer. As soon as you walk through the door, you should first notice that the inspection application. From there, you can start ordering kiosks where you answer anything from when you push your order to when you get your meal should take around 3 minutes.
All of the recipes are developed by human chefs, they're meant.
So you figure out what station.
This is pretty intuitive, okay, we're just gonna try this.
You'll see the last 4 sections, all of them vegetarian, vegan, gluten free.
Well, I need to,
So the bottom.
how's it different to cook with a robotic kitchen than it is to cook with your hands, so.
Well, I had it's very broad for customization for a lot. I had to apply basically one thing that should probably stop me.
We're gonna try that.
I was just put your own twist on it. And we allow you to put your own twist on it without messing it up.
Then you put money down to the skull.
Something I really think that's this bowl, the our did check that goes on our keto style. This one,
This looks really good to me.
this is our cucumber salad.
We can add that as well.
We have choice on the grains.
This is our order. There's one thing, proper vegetable and sauce. To get started, a robot runner picks up ingredients to selected from their individual powers. The runner starts at the bottom of the food meal and draws out the ingredients. The grains are categorized in by content and the seed. The rocks are heated by individual heaters if you send their fields. Even though food gets hot, the heaters stay cool to the touch. After bowl is done, the rock tips downward to plate the food. From there, the cook grabs it to put on the finishing touches. While that happens, the rock tilts down and is in the jackpot soup to heat it before it starts to move dancing. All allergens are outside the box, so there's no risk for cross contamination. So I just got my bowl.
Okay, it should be good enough. So at least you have an idea of how to build or construct that smart restaurant and with the use of IoT technology, right? So maybe in future you will see more restaurant will be like that one. Okay, and then how's about application of IoT in medical health domain, right, or healthcare domain? Okay, so in particular in hospital environment. Okay, so then you will see there's a lot of need for us to collect the data from the patient and then share the data among the nurse and the doctor, etc. Right? So I guess I have a very little bit medium.
We are making no secret of the fact that we are determined to head right to the top of medicine. That's what we're doing. This is a beautiful example of it. I saw a machine that I see several years ago in a lab building in Europe at Siemens, which was now out. And when somebody explained to me how it was going to be different, what were we said about?
We had this vision of what we thought the future of the operating room should be, and what the future of surgery should be. And having an administration that supported this future vision, we were able to, with a lot of people's help, create these rooms, which are not only operating rooms that have a state of work, but operating rooms of the future, where we're going to actually change what surgery is.
We're the first hospital in the country to have 2 of these units in the operating room. Just the whole concept of what is surgery or what is needed to treat diseases is changing. We're going to redefine what a surgical specialist is. Because a surgical specialist now has to be an information technology expert. They have to be a radiologist, endoscopist. They have to be in invasive surgery. They have to be
This is revolution.
Okay, it should be good enough. So at least you see in the healthcare care sector or in hospital, we have a living room for the patient. We also have an operating room for doctor, right? So then we need to collect data, interconnect all the medical equipment together. Then you see we can make use of IoT, okay, to achieve this goal. Obviously, industry, okay, in session 2, we know what is manufacturing system, what is production system, what is automation system, right? So that should be a big area for us to deploy IoT technology, right? Okay, so then you see factory of the future. What should be the factory of the future? Just as I mentioned today, we have an industry 4.0. What should be industry 5.0? So robot integrated the manufacturing channel, right? So eventually you may say it's unmanned the factory. Once you achieve an unmanned factory, then you must put in robot, right? Replace human being, then eventually it could be okay. RIM, robot integrated the manufacturing. Okay, so you just think in this way immediately you understand that IoT is extremely important, right? So look at this picture. You have a robot, you have a human being. So all the equipment must interconnect together, right? Typical scenario. This is one more illustration. You see, you have a production line, you have a robotic arm, you have a mobile vehicle, blah blah blah. All these things, okay. And also you have an office in which you have admin staff doing their work. So all the data must flow into a server. Then people or manager could retrieve all the data, etc. Right? Okay. And then what is industry 4.0? That is deal with the level.
Let's see the next one. What does the industry of the future look like? Our experts have been investing in these strategies for years. The complete digitalization of the manufacturing industry playing a key role in the process. One, that's simple. In the future, it will be more important than ever to operate quickly, flexibly, and cost effectively. Product life cycles are going to be increasingly shorter, while product networks are becoming progressively larger. Just like larger companies, small quantities must be produced economically. Lead times so it's become faster. The companies looking into the future, they must demand their organization much more rigorously to meet customer needs. This can only be achieved if companies start today to digitize, automate, and allow interconnect all processes. Possibly but also along the entire value chain. This means the convergence of the various segments, customers and business partners are part of the process. This will report relevant data and more payments and be able to control the whole network of value creation in real time. Nothing involves the production development all the way up to production and logistics. Of course, data security must be assured at all times. Synchronized physical value streams not only increases productivity of companies, but also efficiency, quality, and innovative capacity. The industry 4.0 concept is new, but unlike before, we now have knowledge and technology for it to become affordable reality. As you can see, the industry of the future presents us with many opportunities, challenges, and questions.
Okay, it should be good enough, right? So now you will know the exact nature of Industry 4.0. Industry 4.0 means IIM, Internet Integrated Manufacturing, right? Clear. Then how about the agriculture, right? So today, I guess in China, the government has paying more attention to the development of technology which will support agriculture, right? Because without agriculture, what are we going to eat, right? Without the food, we may have trouble to survive, I guess. Without the handphone, without the computer, it's okay. We can still live on Earth, yes or no? But without the food, without the drink, how long can you survive on Earth? Right? So this is why we should not ignore agriculture, right? And priority should be given to the agriculture, right? Clear. So this is also an area for us to deploy IoT. Why is it so? I do not know how many of you pay attention to the physical condition for the plant to grow or for the rice to grow. There are two critical parameters very important for all the plant to grow. Number one is what? Number one is temperature. Yes. Number two is what? Humidity. Alright. On top of that, you need to supply nutrition. It's like for us to survive, we need to eat, right? So the plant, vegetable also need to eat, yeah, right? And therefore, we call them as a nutrition, right? So nutrition include water plus other substance, chemical substance, right? So because plants are also a kind of a life, right? So they also need to eat, and they also need to have a good environmental condition like the temperature. If temperature is no good, they will die, right? If the humidity is no good, they will die, right? Then how to monitor humidity, how to monitor temperature, how to monitor the water level or supply of the nutrition? Answer is what? IoT, right? Because normally the farm is very big, right? If you hire a person to monitor, it's a lot of work, right? Yeah. So you just set up a massive network of IoT done already. Okay, clear. So this is a very, very interesting, important domain for us to apply IoT. We should not forget about the agriculture, otherwise we may have a shortage of food, okay, in the future, right? Yeah. So this is another illustration, right? Monitor temperature, humidity, blah blah blah, all this, and also the supply of the nutrition to all the plant, etc. Right? Yeah. And this video is interesting, right? Traditionally, we believe in order to develop a farm, we must occupy a lot of land outdoor. But this is called what? Vertical farming. Interestingly, inside a building, we may be able to produce the food, right?
The leafy greens are growing in huge quantities to be sold to local supermarkets and restaurants. This is Arrow Farms, a massive indoor vertical farm in New York, New Jersey.
Our mission is to build farms and cities all over the world so people have access to fresh, great tasting, highly nutritious food.
Crops are stacked more than 30 feet high inside this 30,000 square foot space. They're grown using aeroponic technology.
Typically, indoor growing roots sit, water and flush our oxygen in the water. Our food vendor realized that if we miss nutrition to the root structure, then the roots have a better oxygenation.
Arrow Farms said the root boosting system allows them to use 95% less water than regular field farm. They also use no pesticides or herbicides. Instead of soil, plants are grown in reusable cloth made from recycled plastic. And instead of the sun, there are row-to-rows of specialized LED lighting.
A lot of people say sun is waiting, plants need sun. In fact, the plants don't need those things, so we're able to reduce our energy footprint by doing things like reducing certain types of spectrum.
This sophisticated climate control system cuts the growing cycle in half. It's a process we grow all year round, but with a much smaller impact on the environment.
There's all these stresses on our planet. 70% of our freshwater contamination comes from agriculture. 70% of our freshwater usage goes to agriculture. 1/3 of our arable land has been degraded in the last 40 years. All these macro trends point to the fact that we need a new way to feed our planet.
One of the early champions of vertical farming is Columbia University ecologist Dixon DePommier. In 1999, DePommier and his students proposed that vertical farms could feed overpopulated cities while using less land and less water. They would also cut greenhouse gases by eliminating the need to transport food over long distances. And the idea is finally taking root. Over the past few years, vertical farms have sprouted all over the world, including in Vancouver, Singapore, Canada, the UK, and around the US. Here in New York, Arrow Farms is building out another big farm, called Steel Mill, one that's bigger than a football field. One that's fully operational is expected to produce 2 million pounds of greens a year.
Okay, this should be good enough. So, I do not know whether you have paid attention to the explanation inside the video, right? So, what should be the advantage for us to promote vertical farming? So, just now, besides the control of temperature, humidity, there's another important parameter is the control of lighting. Without the light, could we grow the vegetable, grow the plant or not? Without the light, answer is no, right? So with controllable lighting, there's advantage about the control of frequency of the light or color of the light. Certain plant means certain type of color in the light, right? So that is advantage. Another advantage is what? It's very important. He mentioned that we are able to minimize the pollution due to agriculture. So in the video he mentioned, okay, the environmental pollution actually come from the agriculture because we put a lot of chemical substance to help the plant to grow. Actually, that pollute the land. Okay, he mentioned this. Okay, so with the vertical farming, we can minimize the pollution to the environment. Right. Then another advantage is what? To reduce the workload of transportation. If let's say you rely on the land to grow the vegetable, then certain area you have a big land, right? Then in the crowded city, then you must use transportation of green, all the vegetable, food, etc. But with the vertical farming, then locally inside the city, you can produce the food, etc. Right? So it's very important. I guess vertical farming could be the future scenario, right, for big city or etc. Why not for every home in future? If let's say you have a flat apartment, maybe one room is like a mini farm, okay? So for you to grow your vegetable, etc. Okay, just I mentioned this one. I guess in future, this should be compulsory for some important building, especially in school, right? There are so many students there, and or for crowded area, for crowded area, it's like in the shopping mall, etc. IoT should be put in place, right? As a government regulation, okay? But in the open land, how to monitor the earthquake, fire, and accident, etc. You can use IoT, but this is obvious, right? In the traffic condition and if there's a natural disaster. But how's about the inside the building or some specific building or strategic location? This is very important, right? Okay, so and inside a city, because in future we may want to transform all the city into smart city, right? Then how to transform today's city to become a smart city? The only way is what? IoT. Smart means what? You must have a brand, the brand of the city, the brands are aware of a certain situation. How to gain the awareness about the every corner in the city. The only way is what? Put the sensor help you to gain awareness, right? Okay, so this is the scenario. You see, inside the smart city, we must have a smart street light, smart health, smart building. You see only smart, right? Internet of sensor, smart traffic management, etc. Smart home, you see, smart environment, right? Okay, so you see, there's a lot of opportunity for us to deploy IoT, right? So now you understand IoT is extremely important. Okay, this video showing you what should be the scenario in the year 2050, right?
70% of the world's population will be living in cities covering less than 2% of the Earth's surface. Never have cities been so challenged, and the trend continues to grow. This raises many issues. Pollution. infrastructure access, traffic congestion, mobility, safety, and the health of residents are only a few examples. The development in combination of new technologies, such as the Internet of Things and artificial intelligence, offer a multifaceted solution for smart city. Smart cities are hyper-connected cities, technologically equipped to improve the lives of their residents. In Mexico, some neighborhoods are still struggling to get permanent access to electricity. So the city installed sensors to analyze the use of electricity in various sectors, so as to optimize energy distribution across the grid. As a result, less frequent power cuts and better distributed energy. In the United Kingdom, the city of Bristol created the Data Dome, a public platform where information on traffic, air quality, noise, or even the city's governance can be shared. They want to grasp the city's goals by exploiting this data. Only local players, citizens, and entrepreneurs can means to build a smart city that truly suits their needs. At AXA, we want to provide our know-how to enable public authorities, businesses, and society as a whole to better anticipate the future and thereby protect all actors living and creating cities of tomorrow.
Okay, should we go enough? So you see, there are a lot of opportunity room for or role for you to play in future, right? Let's say you want to transform base a city into smart city. There's a lot of work that needs to be done, right? So that means a lot of opportunity for all of you to play a very, very important role, right? Okay, since IoT by now, I guess you should be convinced by the importance of IoT. But to a certain extent, in future, if we go beyond the Earth, look at our solar system. We can link all the planets together, China. We can launch the satellite or the space aircraft to land them on Moon, on the Mars, right, or other planet. Can we build the IoT for the whole solar system? Right, so you can think in that way, but actually today we have an initiative about living on Moon, on the Moon, China, in Europe. So they have such a project, right? How to build up residence on the surface of the Moon and send people to live there, right? So this could be a first step for us to jump into Mars, right? So you see, so the IoT in future could go beyond the Earth, okay? So IoT is so important, then we want to know, okay, how to become an expert or professional engineer in the design of an IoT product or IoT system, right? So what should be the engineering foundation? Actually, it's not so complicated, okay? Good news to you is, as long as you understand what is a microcontroller, what is sensor, what is the actuator, done good enough. Okay, so you see, okay, there are different stages. You see, first, you pay attention to this cylinder, right? There are two major devices. You see, stage one, sensor, actuator, right? Okay, second one is stage two. How to link all this together? Answer is what? Microcontroller, right? So you use microcontroller, done already. Stage three, you see Edge IT. Edge IT means just in computational unit to enhance the data processing capability. And then in future, you may have heard of this Edge AI. Edge AI means distributed AI. I mean that each node, eventually you may have a little bit of intelligence. Clear? So sensor, actuator, microcontroller, then if you can have formula in distributed computing system, Edge IT, right? Then lastly, you must have a server, stage 4. You must have a centralized server to collect all the data together, right? That became like the brand of a city, brand of the factory, or brand of the hotel, whatever, or brand of the production line, etc., or brand of the hospital, etc. Right? So these are the stages for you to build up okay, your IoT system, right? So at the starting point, immediately you need to know what is the sensor and what is actuator. Okay, you see the layer number one, okay, IoT device, okay. Based on this description, at the beginning, I mentioned to you, a robot could be considered as a mega actuator. A robot could also consider as a mega sensor. A car, you see, a car is there. A car also could be considered as a mega actuator. A car could also be considered as a mega sensor because car has a sensor terminal. How do I know the temperature distribution in the city? The easiest way is what? If I can let the car to tell me what is your actual temperature, if all the maker can send the temperature data to a server, then I can immediately plot out the temperature distribution in the city, in Beijing, in Shanghai. Understand? Okay, so it's very easy to achieve, right? Just build up connectivity. I can in real time monitor temperature distribution in Beijing, Shanghai. Yes or no? Right? Think in that way, right? So why not to do that? Okay, so this is a open up your mind, right? So once you have an IoT device, on top, try not to be impressed by all these protocol, MQTT, HTTP. I guess you are familiar with the HTTP, right? All these are the high-level protocol of communication. So we are not going to study that one. We only going to study the foundation behind MQTT, HTTP. With all these basic communication protocol, you can invent your own version of HTTP because HTTP is a higher level protocol of communication adopted by people, right? But if you want to compete with this one, you can propose your own, right? It's not an issue. Clear? So you must understand the fundamental principle of data communication, the universal one, universal working principle. Then all the higher level protocol can be invented by yourself, right? Always, if you want to challenge them, okay, you come up with your own version. Okay, so we are not going to study all these specific type of, right? But it's not so important, right? As long as you know at the lower level, with today's microcontroller, you can build up your own network good enough. Okay, so then what should be the sensor? So here is an example. We are going to do the study in one of the remaining sessions. We will cover this one, give you some typical example, right? So this slide help you to understand that we have a whole range of sensors. So this is the big family, right? And at least this help you to understand sensor industry is very important, right? So it's one of the pillar of economy in any country. But you see in Chinese community, we do not pay attention to the small sensor, right? We always like the big sensor. This is a cultural characteristic of Chinese people, right? Pay attention on the small sensor actually may create a big wealth for the country, right? Okay. Then for actuator, it's the same. We have many type of actuator. We have electric actuator, hydraulic actuator, numeric actuator, etc. Right? And if you consider all the car, all the robot as a mega version of actuator, actually this is also a very big family, right? And you see, you can also treat all the machine as a mega actuator. Actually, it's a big family, right? Clear? Okay. So that gives you an idea about how to become professional in doing the design of an IoT product, IoT system. So it means what? You need to have a basic understanding about the sensor, basic understanding about the actuator, basic understanding about the microcontroller, right? Okay. So then you may want to know a little bit about the future challenge faced by microcontroller. I guess the one of them should be energy consumption. Because eventually for some application, you may have a massive network of sensor, massive network of actuator. Then all these devices will consume energy from them. So one challenge is how to design low power consumption device. That means you do, if let's say your sensor consume a lot of energy, then you are in big trouble. Then you keep changing the power supply, right? So big headache, right? So, and one interesting solution is to leverage on the renewable energy, this could be a challenge, right? How to overcome is, why not use solar energy, right? That means you include another device into the T, okay? Because here you never mentioned one specialty is energy harvesting device, like the solar panel, small one. Understand? You just consider that you have a sensor, you have an actuator, you also have a renewable energy device, right? Then supply the energy. This is the solution for you to handle this number one challenge of power consumption. Number two challenge you need to pay attention, but this is quite easier to handle. You can do the encoding, but pay attention to this. This is extremely important, security. Because just imagine you have a massive network of actuators. They are doing good things. If someone hack into the network, then it means what? All the actuators could become a killer. Yes or no? Once you have a massive network of doing good things, right? Robot nicely work. If I hack into there, then all the robot become a killer. Yes. Then you will mess up the entire country. Yes or no? So, but pay attention to this security because if the IoT fall into the hand of your enemy, then you will be in big trouble. Yes or no? Right? But sometimes they say better don't have it, right? If you do not have, then you will not be in trouble, right? But once you have this, you are in the a situation, okay, because you will expose yourself in such a threat, right? So security is very important. You must make sure that your IoT is 100% secure, right? So the encoding, coding, encryption must be there. Okay. Last one is communication real-time performance. Because once you get when you have massive network, means what you have a lot of data, and all the data will make your communication network jam. It's like traffic jam, data jam, right? So, and how to overcome this? Then immediately you understand the data compression is very important because today I guess not many people pay attention to data compression. Okay, so you see our storage device become a gigabyte, and the TB terabyte. You see, maybe 20 years ago, look at the hard disk capacity is what? 20 megabyte, 20 megabyte. Today, one of your files is 20 megabyte, right? Yeah. Because in that day, how come with a small capacity, we can do a lot of things? Compression, okay? So to address this real-time issue, always remember, right? Because when you transmit a big data, then you will make your IoT jam, right? Traffic jam, data traffic jam, okay? Clear? Okay, this is just for you to know how to handle the challenge.
transformation is so extraordinary, and it's sort of all the meaning that they don't know. That's still there. You just need to follow my code. So, like today, producing the car that involved, customer systems that each one can do individual options. So systems and will section of production. A car consists of many thousands of individual parts. That's how processes flexibility. In order to see the demand and unintended, see. This is how it is which Caroline belongs to which customer work. The initial also see the direction of the system work. That's absorbed. We also need to study the technology. With the government and innovation at a site. This future open source.
Okay, so then, okay, so previous one showing you see the real example of the application of IoT in automobile industry. Then you see a lot of robot and even retrieve information about all the car, right? So eventually for each vehicle, you will know the identity of each individual car. Who are the manufacturer, who are the supplier, all these things, all right? So through the use of IoT, you have all the data, etc., right? Then for how to achieve this industrial 5.0, then you see still a lot of challenge. Okay, in order to replace a human being to achieve an unmanned factory, the remaining challenge is what? Strictly speaking, today's robot, okay, in Chinese robot means what? Mechanic man 就是什么？机器人，对不对？ But you must think, is it full man or half man? Because the human being, we have a skill, we have intelligence, yes. But today's robot, if you use this man, 机器人，应该是半人是吧 ？half man 是什么？ Because today's robot they only have one motion. How about intelligence? Alright, so this helps you to understand the challenge faced by robotics. Strictly speaking, today we have 机器半人，应该这样讲，对不对 ？Right. So then, in order to achieve robot integrated manufacturing, the robot must match with the performance of full capability, match as close as possible, full capability of a human being. Then you can call it as a 机器人 otherwise it's a 机器半人 right? Half a human being of mechanized or half a mechanized human being, right? Clear? Okay. Once you think now we immediately understand the remaining challenge is what? AI, right? There. Okay. So that's about the lecture one. So by now you know what is a network system, right? And you also know what is a IoT. IoT is a network system in which the T refers to sensor, actuator, microcontroller, or eventually it's good to aid in the renewable energy device because the energy supply is a big issue, right? But to handle security, I guess it's not big issue, but you pay attention, okay, maybe your IoT secure, right? Then you also know the wide range of application of IoT. In future, everything is IoT, your building, your hospital, your restaurant, your agriculture, your industry, right? And your city, right? So everything is IoT. And then you know a little bit the challenge faced by future IoT, right? Okay, maybe we take a break of 5 minutes, and then we continue, right? Okay, so we move on. Okay, by now we know IoT is very important, and also we know roughly what are the major items inside IoT, right? In particular, we need a microcontroller, sensor, actuator, right? So now we zoom into the detail about the solution, which will enable you to develop first, the network for IoT, then you need to know how to attach sensor into your IoT, and also how to attach actuator into your IoT, right? So in today's session, we just study the solution or universal solution which will enable you to develop the network inside the IoT. Remember, universal solution. Based on this solution, on top you can define or create your own protocol, high level protocol of communication, right? So at the lowest level, you have two options to develop your IoT. One is to apply this universal solution named as a synchronous serial communication protocol, right? Another one will be asynchronous serial communication protocol, right? So in lecture 2, we just cover the working principle of synchronous serial communication protocol, right? Once you know how it works, and the good news to you is you do not need to implement the synchronous serial communication protocol because all the commercial microcontroller has a built-in implementation. That is a good news to you, John. Then you just need to know how to use okay, the built-in solution, okay, for synchronous serial communication. All right, now you must put your mindset, start to change your mindset already. Okay, so in the session 1, session 2, your mindset is like a student, you learn new knowledge, right? Now, from now on, you change your mindset. Okay, you put your mindset as a user. Now we are going to learn skill, more towards the skill, how to use existing device, right? So also we are going to go through the knowledge, the working principle behind this built-in solution, right? So, but it's just to help you to know how it works, okay? But focus is on the skill for you to use the built-in solution inside existing microcontroller. But here we will use ARM Cortex M-series microcontroller as an example because it is the most popular microcontroller, right? And it is also a 32-bit microcontroller, very, very powerful. And this microcontroller is very cheap, John. So this microcontroller gives you the best performance price ratio, right? Very cheap, very powerful, right? So it's like when I teach our student in NTU, so I always remind them, right? So it's like when you buy a cheap microcontroller, try not to believe that this microcontroller is easy to use. It's like when you have something very cheap, you cannot expect too many functionality, right? But for this one, it's an exception. I always tell our students, right? It's like when you pay a price of a bicycle, you get a sport car. You know the situation, so you must be ready, right? Okay, the price of ARM, Cortex, and microcontroller, maybe it's the price of a bicycle. But actually, it's a functionality as like a sport car. Okay, so once you see the rich set of functionality, you should not worry, like should not consider this is a big headache, right? You can still drive a sport car like a bicycle, yes, very slowly, 10 kilometers per hour, yes. You should not say I have a sport car that I need to drive it at 200 kilometers per hour, right? You can, but if you are skillful, if not, since you pay a price of a bicycle, you treat it as a bicycle, then your life is easier. Clear? So you must prepare, otherwise you get lost already. So many things to do, right? Actually, a lot of things you can ignore them, right? It's like you pay a price of a bicycle, we give you a sport car, then you should not say, this is no good because it's a big headache for you to have a sport car. But some of you may say, it's very good, right? So clear, okay? So then we move on. This just prepare you, okay, to switch your mindset. Okay, in the subsequent lecture, you are going to learn the skill how to use the built-in solution, right? Okay, so for microcontroller, this slide help you to understand the major background knowledge which are related to the study of the microcontroller. For our student, they are going to spend 1 semester, but for you, you're just going to spend a few hours, right? But it's still okay, right? So you just focus on the application for you to make use of the microcontroller to develop IoT, right? So, okay, and then first solution for you to build up the network inside IoT is this universal protocol named as a synchronous serial communication. Then you see synchronous serial input, synchronous serial output, then the built-in solution by ARM, Cortex, and Ford, right? But they use this terminology SSI, right? Synchronous serial interface, but it's the standard terminology in industry. Okay, so you just consider this as a universal solution. Okay, for you to achieve data communication at the lowest level. Okay, regardless what is the built-in solution, the principle always the same, right? So on top of this solution, you can invent your own version of a high level communication protocol, right? So the knowledge or the skill about the use of the SSI is extremely important. Okay, so first I will go through the working principle. This just help you to understand, okay, the working principle for the microcontroller to do serial communication, right? Then slowly, then you know, okay, what is the built-in implementation of this solution. Okay, first you need to know, you see the keyword synchronous, right? Do you see the keyword synchronous? So then you must pay attention now. What do we mean by synchronous, right? So that means your action, regardless of what kinds of action are must synchronize, right? So I'm going to show you this impressive demonstration, right? Without the synchronization, they will collision, right? Now you see this demo.
It graphically illustrates the expensive of high speed, high accuracy, synchronized motion.
You see there's no collision here.
The rig contains 3 linear servo axes,
Slow motion.
A rotary servo axis is mounted on each carriage. At the heart of the system is a typical Q PLC with a Q172H motion controller and 6 servo amplifiers. All MRJ3 amplifiers with inbuilt SSCnet3 communications capability. SSCnet3 is a fiber optic network unique to Mitsubishi Electric. It provides high-speed communication between the servo amplifiers and the motion control CPU with data transfer rates of up to 50 megabits per second. The amplifiers used on the servo demo feed are normal MRJ3B models, which are more than equal to the task of running an integrated automation system with our complex synchronized multi-axis movement sequences. Three of the amplifiers drive the linear servo axes, which are inline mounted Mitsubishi Electric LM series motors. The remaining three amplifiers drive Mitsubishi Electric HFAE rotary axes from the MRJ3 servo series. High resolution, absolute precision encoders on the rotary axis offer 262,144 pulses per revolution output. This allows for extremely accurate control over position, torque, and speed. Operator control and monitoring is provided by Mitsubishi Electric DOT15HI, linked to the PLC through the bus on the back main. It allows high-speed data transfer from the servo amplifiers to the HMI. The design of the MRJ3 series provides easy installation and configuration, regardless of the application. The control parameters are set automatically by the real-time auto-tuning system developed by Mitsubishi Electric. This function continually adjusts and optimizes the control parameters for the current operating conditions.
Okay, so this is a very impressive demonstration, right? So now you understand, right? Action has been synchronized, motion has been synchronized. How to achieve a synchronized motion? Answer is what? Synchronized communication. Without the synchronized communication, how are you going to achieve a synchronized motion, right? And then you see the high-speed motion is not the issue, right? So as long as we are able to synchronize data communication, then we can synchronize a lot of action. Okay, so like in that demonstration, you will see three motors must communicate data, otherwise how to synchronize? You must know each other, right? Okay, then you may want to know how do we achieve data communication among the different devices, right? So one popular solution is to transmit the data bit by bit. Okay, for those of you without the computer science background or electronic engineering background, this is just for you to know, right? Digital data consists of byte, yes or no? What is the basic unit of digital data? Answer is what? Byte. Okay, how many bits inside one byte? Answer is what? 8 bits. Clear? So this is the background knowledge, but for those of you, if you do not know, then remember this. Okay, basic unit of data should be 1 byte. So if you have a big file, then you say how many byte, how many byte. You may heard of a gigabyte, megabyte, terabyte, byte, B there. Okay, 1 byte is how many bits? 8 bit. Right now you see shift register normally is an 8 bit, right? Okay, so when we talk about the 32-bit microcontroller, means what? At the one time, the microcontroller can handle the transfer of a 4 byte. 4 byte consists of a 32-bit. Clear? So these are simple mathematics, right? So we have this special memory. We call it as a shift register. Shift register is under the control of a system clock. Okay, this is a background knowledge for those of you if you do not know a digital system. Okay, remember this. So you have a heartbeat, like a heartbeat. A human being has a heartbeat, yes or no? If you do not have a pulse, means you die already, yes or no? Yes or no? If you do not have a heartbeat, means what? You die already, right? So for digital computer, it's very surprising, all the digital computer has a clock, has a heartbeat, right? So all the actions synchronized by this clock. Once there's a transition from low to high, it will do one action or shift out of one bit, something like that. Okay, these are the background knowledge in case if you know nothing about digital computer. Okay, remember this. Okay, conceptually is very simple. One pulse shift one bit. That's it, right? So it's like our heart. We have a pulse, right? So based on each pulse, then our body knows what to do, etc. For microcontroller, it's the same. So you have a clock, then he supplies the pulse. When one pulse appears, then one beat will ship out. Here, okay. So this line help you to understand how to ship out the series of a beat. So it means when we are going to communicate one byte, it means what? We need to have an A pulse. One pulse, one beat, one by A beat, and the A pulse. These are very simple concepts, like it's not a big science, all right? So, okay, it's just for you to know. And how it looks like the shift register. Shift register basically is like this kind of connection, but this I'm going to show you 4-bit serial in, parallel out, or serial out, it's up to you, right? So you see the output of one bit connect to the input of another bit. Okay, and then they connect in CV. So it means what? When one pulse appear, then all the bit will shift one position down. That corresponds you shift out one bit, right? So if you send the A bit, then one byte will shift out down the bit. If the output of this CV connect to the input of another shift register, then one side will shift out, and another side will receive. Clear? Okay. So this is this one. Then you put the two 4-bit together, then you have one byte. This is the basic unit of data inside any digital computer. Then for 32-bit microcontroller, eventually it's not 8-bit, like 32-bit, right? So you have a 4 byte aligned together. That's it, right? So conceptually, it's not difficult. It's just for you to know. Okay. So then, if you have more than one byte, how are you going to do the communication of this 1,000 byte or 1 million byte? How to do it? This is illustration, all right? So regardless of how many bytes you have, you just send the byte by byte or 1 byte to the shift register. After 8 hours, you copy over another byte, then you repeat. Okay, if this operation is running very fast, then in a fraction of a second, then you get the impression all the data sent out in real time. Clear? So this just help you to understand the operation, synchronized operation inside a microcontroller, right? This help you to understand that one side you transmit and the other side must receive. Right? It's always in pair. One guy is output, another guy must be input. Otherwise, your data will go in the air, right? And you are lost. Okay. So then you see you have a master slave. That means you have a two devices, right? You know the connection. Output of the slave is connected to the input of the master. You see the SPI master, SPI slave, right? So output of one shift register will be the input of another shift register, right? So when the clock signal come in, then actually you will see all the byte will pay, right? Okay, after 8 pulse, then one byte from one device will appear inside another device. Okay, this just help you to visualize dynamically the behavior of data communication. Okay, which follow the working principle of bit by bit, right? Bit by bit, we call it as a serial communication principle. Okay, and then this is more detailed about the timing control. Okay, because when you send out the one, okay, this is another background knowledge. Okay, all the digital data consists of 0101, yes or no? Right? The physical implementation of 0 means what? 0 volt. 1 means what? 5 volt. Yes or no? Okay, you understand this background knowledge. Then in the data line, if let's say you make a transition from 1 volt to 5 volt, where this transition take time. Physically it takes time, right? So this is why you see all this the drawing, like you see the transition, like a cross or something like that. So that indicate you need the old. How come this guy? The main projector does not appear. Okay, so basically it means you need to have a little bit of time now for the data to stabilize. So how to provide this time now? So you see, one clock has a positive pulse, negative pulse, a certain duration each cycle, each clock signal, right? Each pulse has a duration. So we will play with this duration. Let's say, for example, when there's a transition from logic high to logic low, right? If we say in this case it means what? To send out the data. Then to read in the data, we must wait for the data to be stabilized. Then you see the reading will be wait when there's a transition from low to high. You see something like that, right? We call it the foreign age or license age. You see terminology for each cycle, you have a license age, a foreign age, right? And logic high, logic low. So if they say foreign age, you send out the data, then reading data will be license age. See, you give a duration of the half cycle, right? For data to be stabilized. Clear? So this will help you to understand the time control inside the digital computing system, right? Yeah, okay. So then this is the illustration for you to see, okay, how to produce the powers, etc. Right? So this is not a big deal, okay? And then for data communication, this is just typical scenario. You have a transmitter, you have a receiver, right? And here basically telling you that you may have three type of communication scenario. One is easier for you to understand. That means always in one direction, very easy. Always start from A to B, very simple. This is one. That means, for example, A is a sensor. He always output. He never receive any as a input. So this is the one type of communication. Second type is A, B. A would be sometimes is a transmitter, sometimes a receiver. Then they can change the role, right? But at the each duration, there's only one direction. That means one communication in one direction. Okay, this is the second scenario. Third scenario is what? This case. That means at any time you can undertake input, output, right, independently. So now you see that means a master device, slave device, right, can do input, output in parallel, right? So then in this case, you ask yourself, how many data lines do you need to have? If let's say you have two devices, you need to do exchange of data, which could occur in parallel, input, output. Answer is what? How many lines? Two, John. Yes or no? One for A to be output to B, another one for B to be output to A. Yes or no? Okay. And since the data communication must synchronize, then you need to have another dedicated line for synchronization. Yes or no? All right. So then in this case, the minimum number of data line or wire, minimum number of wire should be 3. Yes or no? All right. So this is a very important parameter, right? So you need to have a 3 wire connection between two devices in order to implement synchronous serial communication, right? So then immediately you understand what is the drawback of this working principle. If the two devices 1 kilometer apart, and the distance between A and B is 1 kilometer, then the length of your wire is what? 3 kilometers. Yes or no? Total length of the wire 3 kilometers, right? It could be very expensive. Yes or no? If it's 1,000 kilometers, then you need the 3,000 kilometer wire. Yes or no? Can we reduce the cost? Don't use 3, usually use 1. The answer is yes, right? So you reduce the cost by 2/3, yes or no? Once you reduce the number of wire from 3 to 1, that is a asynchronous serial communication. This is the second solution, okay? But this is good for short distance communication channel, not very long, right? Short distance. Eventually the distance is less than 1 meter. If it's less than 1 meter, okay, it's a big deal for you to reduce the number of cable. It's very short, then it's not a big deal, right? Okay, yeah. So this is still very useful for short distance communication. Okay, and some of you may have heard of this I2C, but this is only for very short distance communication. And then you will see we have a two. Okay, for this one, there is only one data line. You see serial data, SDA. Then you have a serial clock. Okay, so this means what? This is the second scenario. At the one time, you can only do one directional communication. You cannot do communication in parallel. Okay, this is another scenario. Okay, so the one time you can only communicate data in one direction. Okay, because you only have a single serial data. You see, serial clock is a signal line that provides the synchronization. This just help you to understand the physical construction. Clear? So this is a typical application scenario. Okay. Then in this case, you may want to know, let's say for the master 01, if you want to communicate data to slave 03, how to prevent slave 02 to receive data? Alright? So these are the considerations. Then solution is what? When you communicate series of a bit with one session, right? So you must keep the address information. What do we mean by address? Is the ID of the receiver. Now you see device address, all right? And then eventually you can tell the receiver where to put this data. After that, you only send out the data AB. You see, that means in one session, it's not to communicate a bit, you communicate 32 bit, yes or no? Then first A bit has a certain meaning, second A bit has another meaning. The last A bit should be the data, right? So this is the code data framing. It's kind of an encoding. Get it, right? So this can help you to know. So this is the I2C protocol, right? But you can invent your own way, your own protocol, right? There's one session, I communicate ATP, up to you. Then among all these ATP, what is the meaning of internet? It's up to you. Okay, try to be flexible. You are able to invent your own protocol, right? So try to be flexible. Okay, so based on this background knowledge, then you look at how to achieve a serial input, right? So you have an output. In this connection, you will see master input, slave output, or master output. You see MO means master output, then slave is the input, right? MI means when the master is the input, slave is output, SO. You see, slave output, master input. When you do the hardware connection, wiring, you must follow this connection, right? So then you also have a clock signal jump. The clock can come from master or come from slave, that's no matter. Once you do this connection, internally you write the 1 byte into the shift register. Then the hardware will issue a clock, okay, a pulse. Then 1 byte will ship out. That's it. Okay, so this is the working principle. You understand how to communicate 1 byte. But if you continue to send out the 3 byte, then this is the I2C protocol. That's it, right? So this helps you to understand the working principle. But you do not worry because all the microcontroller has a built-in implementation. Then you just know how to use it, right? Because when you use it, you understand why you must use in this way. Okay, actually you can visualize internally what's going on. Okay, clear. But you may say, hey, how come there's an additional cable, right? Friend, that is an additional signal to indicate you are going to undertake one section of communication, right? So additional control, right? So within this one session, eventually you just communicate. So it will be like I2C, okay? So that give you design flexibility. Now you see the SCK is a clock signal. You see clock signal is a regular pulse, right? This is you interpret it as a heartbeat, right? So every digital system must have a heartbeat, right? So for each pulse, you have a foreign age, rising age, logical low, logical high, something like that, right? So and then each transition, that is how we do an action, something. Okay, yeah. Then this is a symmetric clock, right? To output something, that means when one clock appear, then the output device just send out the one bit. It's a shift register, like it's symmetric operation. So this is not a big deal, right? Okay. So then in this case, master output, slave input, or slave output, master input. It's always symmetric. Okay. So they exchange each other bit by bit. Okay. So it's not a big issue. Okay, so that's about the working principle of synchronous serial communication. Good news to you is you do not implement all this working principle because you can buy microcontroller with the built-in implementation. Then your role is to behave like a user, how to use it. Okay, so but now the good news to you is with the low cost. You purchase this Cortex M4, actually you get a very, very powerful microcontroller, right? Okay, so why do we use microcontroller? This just help you to know the answer. You can use microcontroller to serve as a hardware inside the control loop. In section 2, we have study control theory. Then how are going to implement those PID controller, relay compensator, answer is what? Inside the microcontroller, right? So microcontroller could serve as a controller, but in today's session, microcontroller serve as a node of communication, right? For us to build up a network of communication. Okay. So then what is your role? Okay, when you use a microcontroller, answer is what? Your role is not to implement protocol communication. Your role is to use the built-in solution, right? And then you must know why do you want to use the built-in solution. Then in this session, the context is what? You are going to build IoT, right? And for other users, eventually they use this network communication for other purposes, right? Clear. So that means as a user, you know the problem to be solved. You know your solution, your intention, right? Then you just use it. That's it. Very simple. Okay. And in order to use it, you need to know a little bit the working principle of a microcontroller, right? But the good news to you is how to use microcontroller. Actually, you just need to do this 3 steps. First, you configure control register, right? Then monitor status register. Then just get read and write the data from data register. That means you just pay attention to these 3 types of register, right? Or memory location, control register, status register, and the data register. Control register is for you to do the configuration. Tell the hardware what is the exact intention, right? And the status register is for you to monitor, for you to know what is the working condition of a microcontroller, right? So data register is for you to send out the data, receive data, that's it, right? Then how to configure? Actually, just write the value inside a register, okay? And for those of you, if you are not used to this one, you just consider a register. A register is the memory location, right? And then you remember 1 byte is what? A bit. You just consider each bit is a magnetic switch. That's it. When this bit is equal to 0, means a switch off. When the bit equal to 1, switch on. Alright? Do you know, okay, when you go to the console, you see the the guy control the music. You see a lot of switch on. You just imagine like that, right? Okay, so register memory to you is what? Is switch on because inside any digital computer you only have what? 0, 1, 0, 1, yes or no? If you think in terms of 0 means switch off or 1 means switch off, finish, done again, right? So then when you put all the 0, 1, 0, 1 together, you have a number, right? So basically, the way how you want to do the switch on, switch off, basically means what? You just write the one data that correspond to the situation on the on-off into a memory location, done, right? So the instruction for you to write the data into the register, it's just 3 type of instruction. Okay. In case like you do not know the assembly language, it does not matter. You just understand the concept 3 number. Okay. To configure input output device, you just need to know which bit to switch on, which bit to switch off. Okay. And once you know all the bit, the on-off situation, you get the number. Then you write this number into this data register, or risk control register. Here, right? So everything narrowed down to the determination of which data or which number to write inside which register. Okay, like give you the situation of doing switch on, switch off for each bit. Then immediately you understand each bit inside the control register has physical meaning. Yes or no? Right? It's like you turn on the light, you switch on, switch off. Okay? So it's just a background knowledge for you to know. Okay. Just now I mentioned when you pay a price of a bicycle, you get a super sport car, right? And then here you see ARM Cortex M4 is actually cheap, right? In terms of Singapore dollar, maybe less about 10 or less than 50 Singapore dollar, very cheap, a few hundred, okay, 100 or 200 RMB, right? But you get the sport car. You see how many data communication port do you have? 4 for one microcontroller. You have 4 SSI. So that means each node allow you to establish 4 connectivity. Immediately it means what? This guy allow you to build up a matrix of communication network. That means each this microcontroller you have a label in the north, south, east, west. Yes or no? Right? Very, very cheap solution. Okay, 4. And they support 3 industry communication protocol. It's a specific way to implement serial communication, right? And then you also have a buffer. P4 means first in, first out. It's a buffer, right? And the data size, you see, not 8 bit, you can go up to 16 bit for one data. You can say is extended data, right? Having 1 byte is 8 bit, right? You can configure your device as master slave up to you, right? Okay, here you have a big name here, interrupt. Interrupt basically, it means internally generated the signal, right? For those of you, if you do not know interrupt, actually, you should know the interrupt. Okay, I guess every one of you know that when your stomach is empty, your brain knows that you are hungry. Yes or no? I guess every one of you, otherwise you will have problems. When your stomach is empty, your brain knows that you are hungry. Yes or no? How come your brain knows you are hungry? Answer is what? Your stomach will send the interrupt of your brain. That's it. Now you understand what we mean by interrupt. Internal signal. Typical example is what? Your stomach send a signal to your brain. Then your brain know I'm hungry, I must go to the restaurant to eat. Yes or no? Okay. But this scenario is very important. So it's the same. After eating, do your brain will still interpret that you are hungry? No. This means what? Your brain clear the interrupt signal. It's actually important. Simple. If let's say what happens if your brain forget to clear this hybrid interrupt consequences well. You continue eating until you die, right? Same thing happen for microcontroller. Remember this, our brain is very smart. After eating, automatically clear hungry interrupt. Then you will never repeat you eating, right? When you live a normal life. Otherwise, you will die. You keep eating, right? Hungry, you eat, then die. Okay. For this one, Sam. Okay, you need always remember. Once you pay attention to internal signal, your program must clear interrupt. Otherwise, you will keep doing the same thing. Okay, clear. Then it's a similar situation. Okay, clear. Then, in terms of the hardware configuration, it's just for you to know, right? And this is just for you to know to the physical connection. You see the chip itself has a pin number of 64 pin. What do we mean by the pin? Then you look at this table, right? So, another background knowledge is for you to know the port input output. So for ARM Cortex, you have a 6-port. Each port has a pin. That means one port corresponds to one byte. So ARM Cortex M4 has a 6-port, port A, port B, all the way to port N, right? So it's very, very powerful. You can eventually connect to many external devices, right? Here, okay. Then this is for you to determine what is the frequency of the clock for data communication. But you should not ask the question, how come you use this formula? So this is determined by the designer. You just use this formula, right? So as a user, you need to provide value for this prescaler. And then this SSICP SR, this is the name of the register. You need to choose the number from 2 to 254, right? You also need to write the number to this SSICR0 register. Once you, as a designer, as a user, you choose any number, you put inside, then the hardware will compute what is actual frequency of the clock. Okay. Then you can say why you do this way. Don't ask questions because it's like when you buy a car, you should not ask, how come this operation is installed here, right? You just follow the design solution. Okay. But you go to this example, then you roughly know how to use this formula, okay, to do the configuration. Okay. So then for TI protocol, the TI way of implementing serial communication is like this. You see, when there's a rising age, there is a write operation. That means a write one bit to the data communication, right? So you write means a transmit is a TX. T means a transmit to write. To transmit to write means the same thing. Now you see synchronized when there's rising age, transmit, we'll send the data to the physical line. It takes time to stabilize, right? Then read should be the falling age. Right means is rising signal, to low signal go to high signal. After that is a falling age, high to low. Okay, when the right is using the rising age, read operation is a falling age. You see, after half cycle, the data is stabilized, then you can read the stable data. It's very simple way to synchronize the data computation, read and write. Okay. And this one is a continuous transfer, right? You can continue transfer a series of bytes, okay, non-stop until you send a specific signal to stop the communication, right? So it's repeatedly a series of bytes. You see, MSB means the most significant bit, LSB least significant bit. After that, you repeat continue, right? Then you mainly by send out, right? So between MSB and LSB, in between you have a 4-bit or up to 16 bit. Yeah, okay, this meaning, right? Then you repeat, then you can send out a series of data in space, right? Okay. And this is another version of an implementation by another company, like Microwire, then you see read. Okay, now it's inverse. You look at the read To read means to receive. Look at the clock signal is a rising edge, transition from low to high. It's totally reversed. So based on that, it means how to write. Write means when there's a falling edge to write. Read means when there's a rising edge to read, right? You see, when you read, the read line is in the middle of the pillar. It's very stabilized, right? And from here you will see for TI is a big company like Texas Instruments, famous company in the US. You see, you have a TX, you have a RX. This is the scenario of doing bi-directional communication in parallel. Yes or no? Because you have two parallel, yes, right? Look at this one. Is it parallel or sequential? You see, first you do the TX channel. After that, you wait to do the RX. Do you see TX or the pillar? After that, after LSD, then you start MSD of receiver. This means the first transmit, then I receive. So that means that the one time you do one direction communication. Okay, so this is for you to, if let's say you want to do the you have an application which corresponds to this situation, then you choose this implementation solution. That's it, right? Okay. Then continuous one, you see, after transmit, then you do receive. After receive, you go up to transmit. After transmit, you go down to do receive. Do you see this? LSP followed by MSP, then LSP at the bottom, then go up to MSP, then reach LSP, then you go down MSP. You see, you alternate, right? Transmit, receive, transmit, receive. Okay, continuously doing this way. Clear, right? So this is another scenario of doing communication. And this is the one part. There's only one directional communication, right? Not like the TI. Okay. But this one is more complicated. You have additional 2 bit to control the meaning of the first age or second age, as you see, they control. But you can read carefully, but anyway, you do not need to waste too much time on this kind of things. That means this gives you more flexibility for you to choose what to do with the first age, what to do with the second age. But you just need to know this one that looks like a TI. Is a bidirectional communication, right? Transmission and transmit receive can occur in parallel, right? Only difference is when to do the read, when to do the write. You see, to read to be read, right? First age, and this is the first age, right? What is the? You see, this means first age is a rising age. How to define what is the first age? This is the rising age. First age is the falling age. So you have more flexibility. Then you should not ask, okay, how come so complicated? It's like what I say, this looks like a sport car, right? So, but if your application is very simple, you do not don't play with this. Once you have such a requirement, then you play with this, right? This one is for you to define second age. You see, you can use the first age to do the read, or second age to do the read, right? That implicitly first age is a write, right? So you see read write, okay, something like that. But this one you say second age is a rising age, then second age is a falling age. You see, so something like that. Okay, why is this so? Because it's to have more control about when you read, when you write, something. Okay, so more control. Okay, so once you know the background knowledge to use built-in solution, these are the standard steps to configure input, to configure internal process of the hardware, to configure output, and running. That's it. Okay. So configure input. Basically, you need to know okay, what is the system clock, right? So you just write the number here. Actually, you do the selection. So you read the manual. I just quickly go through, just help you to know as a user, you just need to follow all this procedure. Internal process, basically you need to tell, okay, which implementation to use, use a free scale implementation, TI implementation, implementation, microwire implementation. Then you remember the formula, how to do the serial clock rate. You need to write the value inside, okay, this bit to tell the hardware, this is the number you choose. You see, by default, it's 8 bit of data size. It could be 16 bit or more than 16 bit, etc. Right? Okay. So all the detail you need to read by, you just roughly know that. Okay. In order to use the built-in solution, you just configure. Okay. Turn on, turn off all the individual bit. You consider all this as a mechanic switch, switch on, switch off. That's it. Right? Then by switch on, switch off, you know your intention. For example, if you're not behave like a master, you must switch on. If it's slave, switch off, right? And if let's say you use synchronous serial communication, you must turn on. You say, let this node to work as a synchronous serial communication, follow the synchronous serial communication protocol, etc. Right? So these are the then configure output. Output basically. You see this formula, you must write in another value here. Okay, is you write the number, use all this 8 bit, you see 0 bit to 7 bit, okay, into this register, right? Then okay, another just now I already showing you this register. You see this SCR, write another number here, right? Then the hardware will compute what is the frequency of the clock, okay? And here is to, okay, just now I mentioned infrared, that means the hardware is very powerful. Whatever happens, it will tell you internal signal. Sometimes you may say, I do not want to know all this internal signal. You can mask them out, right? So you turn on the bit, that means to stop internal signal, to disturb you, etc. Right? But for some application, you need not to. And then, okay, here you see to clear the interrupt. In case if you pay attention or take action according to the internal signal, you must always remember to clear the interrupt. Example is like our brain. If your brain forget to clear this signal, which telling you that you are hungry, then you will end up of repeating go to restaurant, eat until you die. Right? Yeah. So this is the same situation. Okay. So pay attention. If you care about the internal signal after the processing, taking action or doing something which correspond to this interrupt, always remember to clear the interrupt. Okay. Otherwise, you will repeat the same operation. Okay. Then once you configure, very simple, then you run how to run. If you transmit out, then you write the file to this register. If it's to receive, then you read the file from here. That's it. Right? Very simple. Okay. And you can also monitor whether some internal signal appear or not. That tell you the working condition of the hardware. Then you check all the bits. You see, very simple. Okay. And even let's say in the previous slide, you see I can mask out certain internal signal because I do not worry about internal signal. But during the operation, you can still verify this mask out the internal signal appear or not, right? That means the maximum loss, okay, you still can verify the appearance of all signal. Okay, that's it. And then because the I/O has a buffer, because when communication too fast, your program running slow, then in turn the data will store inside the buffer, right? So you can monitor status of buffer, whether it's full, half full, or empty, something like that. You see, it's extremely powerful, right? Okay, that's it for the second lecture, which is about synchronous serial communication. So we continue. Now you think about the drawback of synchronous communication. Just like I mentioned, you need to have a 3 cable, right? But if you have a 2 device which is separated by 100 kilometers, then the length of your cable is what? 300 kilometers. That is expensive. How to reduce the cost and try to make it to be one single cable? This is the minimum. Can you say I do not have any connection? Can you reduce the cable to 0? If you reduce to 0, means you have island, how to communicate? Alright, so the best result is what? Reduce the number of connection to one cable, yes or no, right? If you do so, this is this solution, right? So all the microcontrollers support this solution. Today, when you send an email to your friend like in China and Singapore, actually follow this protocol. Understand? How you send the email from Singapore to China is this one. Right? You only have a one cable, right? So you see, this is a very, very popular solution for long distance communication, right? Okay, so then what is a synchronous communication for long distance communication scenario? This just I took military, you see, in military application.
Unmanned aerial vehicles, but just like planes. But the pilot stays on the ground. The pilot, anyway, must be perfectly connected at all times. The SMU space has a solution. Based on space technology and telecommunication satellites. Using the 5 GHz frequency band allocated worldwide to aeronautical safety applications. Safe bi-directional command and control communication links are established with the UMP. From the remote pilot station to the ground gateway and the satellite payload to the UMP. Or alternatively, through terrestrial stations using the same 5 GHz frequency band and the same link on or terminal. As to the 5 GHz long-range while maintaining permanent control of the UAV. After taking off using that 5 GHz terrestrial station, a UAV is seamlessly rotating to satellite 15 degrees. Changes as it goes in satellite even possibly in handling to light lights while on route, and it completely transparent showing a statement and the tracking and available at all times.
Okay, it should be good enough for you to understand long distance communication. You can imagine what is the distance from one point on the earth to one satellite. Should be at least 100 kilometers at least, right? So it's a very, very long. So you cannot use established three connection, otherwise it's costly, right? So for long distance communication, you may heard of an internet or this is use this solution. You may also heard of RS-485 in industry. You also use this solution, right? And your fax machine actually use this solution. So you see, once you know how to achieve asynchronous serial communication, you can implement your fax machine by yourself or invent another protocol for long distance communication, right? Then how to solve this requirement of synchronization if we reduce or remove dedicated line for synchronization. Now the solution is what? To A in or stop bit, to A in 1 or 2 stop bit, right? And also to make the data communication to be safe with A in parity bit. Parity bit is for the tracking of the error, right? So this is the solution, right? So you have a data bit, for example, 7 data bit, 1 7. So you know for the keyboard ASCII. So over you type your report, actually all the keyboard, English keyboard use ASCII, ASCII only use 7 bit, right? But in case you have an 8 bit, doesn't matter. So you 8 in 1 start bit and 1 or 2 stop bit plus either have or do not have a parity bit. That's it. So this is the way for you to achieve a synchronization. So the start bit will wake up, indicate the start of the computation. Then the stop bit will indicate the end of the computation. So in this case, you only have a single line. That's it, right? Clear? So this is the solution. And what we mean by parity, you may have an odd parity check-in or even parity check-in, etc. So you just A in the additional bit, etc. So after the formatting, then the total number of bit may be 9 or 10 or 11 or something. Okay, so it doesn't matter. So in this case, basically means you have a series of bit. Okay, but this slide showing you example of enable all parity bit. All means if the number of 1 is not odd number, then the parity bit will become 1. If the existing number of 1 is already an odd number, then parity bit will not be 1, it's 0, right? So parity means either you A in 1 or not A in 1, as long as total number of 1 is an odd number. Okay, even bit, where is the even? It's not here. Okay, then even means the total number of 1 is an even number, same. Okay, so conceptually it's very simple, right? So then with this principle of A in extra bit at the beginning of the data, at the end of the data, and also A in the parity bit, you can achieve a very secure or reliable data communication, right? So then this is the scenario for you to do synchronous or asynchronous serial communication. But here you see you may have a scenario of 2 built-in asynchronous communication. Let's say you see unit A has a transmit, unit B has a receive, unit B has a transmit, unit A has a receive. That means it support 2 parallel asynchronous data communication. These 2 are totally independent, right? Okay, so this just for you to know. Then for input operation, you receive actually you will first receive a start bit followed by data bit, then eventually parity bit. Last one should be the stop bit. So look at the sequence of the bit that the receiver will receive. It's like this. Okay, so you can easily read. For output, okay, always send out the start bit first, followed by data bit, then send out the parity bit, etc. Right? So for output, so you robot A will send out, right? So start bit first, so you follow the time axis, etc. Right? So it's a symmetric operation. Okay. So you see the concept is very simple. Working principle: A in start bit, A in parity bit, A in 1 or 2 stop bit, right? Then you can achieve a synchronization of communication of 1 byte. Then you repeat then you serial very simple. Very simple. In this case, only 1 connection, 1 byte. Done already. Okay. So then ARM Cortex M series microcontroller allow you to implement a control application and in particular IoT, network inside IoT. Okay, then your role is as a user, and remember, if you want to know more detail, do little bit study. But this is the good news. How to use a microcontroller is just to know how to switch on, switch off specific bit. It's like you treat each bit inside the control register as a switch, right? How whether switch on or switch off. That's it, right? So you tell them your intention. Once you determine the situation of on-off, then you know the number, then you write all this number in 1 time inside the register. Done. Okay, yeah. So now you see you pay price of a bicycle, you get a supercar, right? You see how many asynchronous serial communication hardware support for 1 microcontroller. Age, they use UART means what? universal, A means asynchronous, receive and transmit. That means you have you can do parallel receive and transmit. You have an A unit. A unit allows you to build up a three-dimensional IoT, yes or no? Because one unit left, right, and in front, behind, then up and down. You just need the 6, yes or no? Three-dimensional. In the plan, left, right, in front, behind, then up and down. Then you build a three-dimensional IoT with this protocol. Get it? So you see, this is a very cheap but very powerful. You pay a price of bicycle, you get the super car, sport car. Understand? Okay. And look at the speed, communication speed, 5 megabit per second. 5 megabit per second is a lot of data per second. Right? Eventually you can up to 10 megabit per second. Right? Very, very powerful. Clear? Okay. So then, okay, this is the hardware. And if you want to do the connection, if you use a specific power, right? So you follow this cable, then you know how to do the hardware connection, etc. Okay. This is the supported protocol for synchronization. We call it the data framing to frame the data, A in, additional start bit, additional parity bit, and the stop bit, right? So you see, start bit followed by this significant bit is a B0. Start bit followed by bit 0, B1, B2, B3, all the way to 7 or B8. After that, whether you enable parity or not, you A in there. You can also choose to have a full stop bit to make sure, okay, you can make the communication be stopped, right? Okay, so something like that. Once you know this, the remaining is just to configure the hardware, okay? And then you may want to know by default what is the frequency the bit we are sent out. What should be the frequency? For those of you, if you have a player with a fax machine, you need to set up the baud rate of a fax machine, sure or not? 9600, this is popular one, right? So this is the same. Because we remove a synchronization line, then we let the communication device to choose the same baud rate, right? Communication speed. Then how to set this communication speed? You need to write the data into these two registers. I guess there's a formula. Is this formula? You should not ask this question, why we use this to determine the baud rate, right? So just follow this, okay? Then the hardware will know, okay? As long as unit A, unit B configure in the same way in terms of communication speed, downloading, right? So they can synchronize, okay? So then how to determine the value in this register? Okay, you follow this formula given to you, right? And I guess you have an example here. You go through this one, you will understand how to determine the value inside these two registers. If you choose the baud rate, this is an example to choose the standard baud rate, right? You see 115200. This is the industrial standard, right? This is another value of baud rate. Okay, you may have a 9600 is another one, right? So based on it, then you can compute what should be the value right into these two registers. That's it. Okay. So then to operate this hardware or use this built-in solution, okay, of asynchronous serial communication. You see, as a user, you always do the same thing of configure input, configure internal process, configure output, run. Okay, that's it. How to run? You just monitor status register. How to configure input, inner process, output, use the control register. You see, the guideline for you to behave like a user is always the same. As long as you work in this way, then it's very easier, right? So then here I just quickly go through how to configure input for ARM context, right? So then here you will see you need to determine your data frame start bit, how many stop bit, whether you use parity bit or not, right? And also the size of your data. the size of your byte could be 5 bit or 8 bit. You must tell the length of the wall. You see, wall means the general the size of byte, etc. Whether you enable buffer or not, FIFO, first in, first out. FIFO means first in, first out is a buffer, right? You see, whether you want to use penalty bit for checking, error checking or not, you just set it to be 1, then you enable. You see, it's quite straightforward, right? So detail you just read through, and this is a 9-bit mode. I guess this is for you to implement RS485. Eventually, you send out one file, but this file indicates this is an address or ID of the receiver, right? So detail, I guess you can read, okay? What is a 9-bit communication? So use this one, you can build up a network with an address. Okay, so you indicate which module you receive your data, right? Okay, so and self-address you see, it's a 9-bit mode. That is actually this is an RS485 protocol, right? So each device has an address. Then you can tell, okay, this data is for which device according to the address, etc. Right? Okay, so this is for this purpose. Then internal process. So basically, you need to choose what is the system clock, the heartbeat of the microcontroller. So you have option here, right? So you select, and then you want to whether enable asynchronous serial communication or not, right? Because also you can do parallel transmit out and receive in parallel, but you can still say I only do the receive, I only do the transmission. And in case this is the application for the fax machine, they give you an additional enable RTS, right? That is for the use of fax machine, right? So you detail you read, right? Okay, so configure your not. This is for you to set the communication speed, right? So you follow this example, okay? So you must write the data to compute based on the baud rate. What you can choose is you cannot choose any value for the baud rate. 115200 is the baud rate in that standard, right? The 16, I guess this one you can choose, okay? You are free. 20 million is depends on the microcontroller, right? So you buy specific one, this is a specification, one is before the frequency of the clock, okay? So based on that, you can calculate this value, then you write into this register, right? And then the integer part, because you must also write the fraction, because once you get the number, you have an integer part plus fraction, right? Integer part write into this data register. For the fraction 0.8507, you must do this computation at times 60 plus 0.5, then you get the integer. Then this integer you write into this data, this register. That's it. That is the way for you to set up the baud rate. And in case if you have an error, then is an error here. Write something here to if there is a hardware has an issue, then you clear the data. Okay. Then for the output is the same. Previous one, because each device can serve as an input receiver, and each device can also serve as output device. There is a symmetry you are setting is exactly like when you set the input operation. Output means a transmitter, right? Input means receive, right? We can do in parallel, okay? So the meaning is exactly the same, right? So I just, and whether you want to enable the P4, etc., right? And the mask out the interrupt or not, okay? Something like that, okay? So then run. Run means just monitor the status register, right? So, and if you want to do the output, the byte to be sent out, you must write into this data, you see one byte right there. Then how will you do the computation? Okay. Then for the P4 status, data empty and half empty, etc. I guess you will indicate to you, right? On this side. Okay. Receiver status, right? So whether you receive or you have an error, whatever, all these flags will indicate to you. Just monitor the status register, then you will know the hardware working condition. Okay, so then transmit, receive, whether transmit complete or not is empty or half full or something like that. So you by monitor all these switch, you will know the hardware situation or condition of data communication, either transmit or receive or something like that. Okay, so I guess okay, this is the internal signal. Okay, you can check all this internal signal. I guess you by reading this, okay, when something happen, it will tell you, right? So by monitor all these internal signal, you know the working condition of the hardware, right? Something like that. Okay, and you can also mask out some internal signal, Then again, you can also verify all the internal signal which has been masked out, right? So you can still verify whether they have been present or not, etc. Right? Okay. Okay, this is just to remind you, it's like just like I mentioned. Okay. For our brand, when we after lunch or after dinner, we all automatically clear the interrupt. Then for microcontroller, you always must remember to clear the interrupt in case if you do something when interrupt occurs, right? Okay, always remember to clear it. If you do nothing, then no need to clear, right? So something like that. Okay, that's all about the today's study. Then the key takeaway from today's study is for you to know the importance of building up IoT, because IoT has a wide range of application in industry, in agriculture, in city, in transportation, etc. Right? So IoT is very important, and the robot is a mini version of IoT. And the production line is a mini version of IoT. Eventually, in future, hospital, restaurant is IoT. Right? Then you switch your mindset into the use of a built-in solution to implement the network aspect of IoT, right? So you use the popular microcontroller, which is the ARM Cortex-M series of microcontroller. Okay, now you know there are two solutions for you to use in order to build your IoT. One is a synchronous serial communication. If let's say your IoT does not cover a large area, like your robotic arm is short distance, then you can use a synchronous serial communication, right? If your IoT cover a large area, for example, you have a communication between the ground station and the satellite, that is very, very long distance communication, right? Then you have to use synchronous serial communication, right? So you just need to behave like a user, know how to configure the register, tell your intention, set up a certain parameter, right? Then the hardware will do the communication for you, and the hardware will also tell you the status of operation through the interrupt. By interrupt means the internal signal. Okay, by monitor internal signal, you know what happens, etc. Right? So that's about today's study. Okay, we focus on the use of a microcontroller to build up the network. Right? So the remaining two sessions is for you to know how to attach sensor to this microcontroller, how to attach motor to this microcontroller, right? So once you know how to attach sensor, how to attach motor, okay, into this microcontroller, then you have IoT already, right? Okay, yeah. But we still have maybe 20 minutes. Then we do a short Q&A for the session 1, 2, and the today's session. Okay, so we just do a short Q&A.